All right.
Assalamualaikum.
Okay. I know that you have a midterm today, so it's not because of you have a midterm, but today my lecture would be like around 1 hour, and then after that you would do like some exercises. Okay, so during that 1 hour of the exercises, ask me the questions so that you would know how to do the exercise. Okay, but even though it cannot replace the final exam question or the midterm question because I cannot check the steps that you have taken. Okay, but okay, you can practice it at home. Okay, so you can practice on how to write it. Okay, based on what I will teach you after this. Okay. Um. So let me start. Okay, let me start the lecture. Start transition, a transcription, and then let me share my screen. Right. Okay, download the lab 8. Okay, download the lab 8. Don't open the lab assessment 8 yet. You don't need it yet at the moment. So what you need is a piece of paper and pencil. Okay. So paper and pencil, and then and as for myself, I would need a calculator because I don't have a calculator at the moment. Okay, so this is the tools that I would need for my assessment today. Okay, so and then don't forget to open your green sheet. Okay, so this green sheet, your cheat sheet. Okay, also your cheat sheet or your toil in Malay, they say, whatever it is. All right, so I'm sure you have downloaded your lab notes. So now let's start with the lab 8. Okay, so it's not that we are not going to touch about the programming, but you need to know about the addressing. Okay, about the addressing, the instruction format before we start with the basic instruction. Right. So by the end of the practical, okay, so students should be able to understand the type of instruction format and its application. And then different type of addressing mode and its application. Also able to demonstrate constant usage in an instruction means that I will teach you how you can encode. Okay, the word is encode the assembly. Okay, encode the assembly code. Okay, the assembly instruction to machine instruction. Alright. So this is what I'm going to show you today. Right. Um. So we are not going to use the QtSpam at the moment, okay, but only that you need a piece of paper, right? So unlike other architecture, MIPS have only a small number. I'm not sure you can see it or not. Let me make it bigger. Let me make it bigger. And then, okay, so I'm sharing it. So MIPS have only a small number of ways that it can compute addresses in memory. So the address can be an address of an instruction for branch and jump instruction, or it can be an address of data. So everything is addressable. We call it as addressable is because everything was referred as an address. So instruction is referred to an instruction memory, and then the data. Okay, the data in the QtSpim here. Okay, if we open the QtSpim, I hope my PC can sustain the load. Yeah. Right. As you can see, okay, so this is where your instruction is, right? And then there is a memory there. There's a memory there. Okay, whereas also the data has a memory and also has a value that they will store on this section. So if you see like this, macam mana nak tarik? It's bugging me. Okay, so as you can see like that, so we can say, okay, we can say the memory is divided to instruction, and then another side is the data memory. Okay, all this is a data memory, instruction memory. So it is on a different location. And it's not contiguous. I'm just feeling lazy to draw it. So there's one side, okay, in the cache become the instruction memory, and then there's one side become the data memory. So everything is addressable. Okay, everything is referred in the addresses. So be it any instruction such as branch, jump, or load and store, everything must be addressed. Okay, so the address can be an address of instruction or maybe an address of data. For example, load and store instruction. So instruction format is not an addressing mode. The instruction format is how an instruction is put together. Okay, so how you format it, how you rearrange it so that, okay, so when the instruction is executed on the processor, okay, when they execute it on processor, okay, so the data would flow based on the, not the data, the bit would flow based on the format itself. Okay, so this you would learn on data path. Okay, so there's a reason for the R format, I format, and G format. Okay, so as I have mentioned on the lecture, we have that R type, okay, which is what we call as register type. Okay, but sometimes they call it as arithmetic type. Okay, arithmetic, and then where does it come from? The R, right? Arithmetic. The R there. That's where it comes from, the R format. Sometimes they call that. Okay, so whatever it is, you just know what is R type. Okay, so R type is any instruction that include arithmetic and logic with all operands in registers. Also, if we have a shift instruction and register direct jump instruction, for example, JAL and JR. So all this is an R type. Okay, so all R-type instruction would use opcode as 000 and then to differentiate, okay, whichever which R instruction it is, it would be put inside the function. Okay, can be seen a different value in the function field. Okay, so this is a field. So R-type has 6 fields. Okay, and then I format is a group. So how do you want to know if it's an R type or not, right? This is where it comes, your cheat sheet, you know. So as you can see, let's say you want to find out what type of instruction is add, okay, or maybe load word. Okay, so for example, if we want to find sorry. I want to find control F, control F. Baru nampak. Aduh dah. Okay. So now I want to find ADD. Okay, so when I type it like that, so it will go to the all ADD that we have. See, ADD. So at the moment we have ADD. Okay, and then this is the instruction that I want to find. So ADD is under R format. So the format is on the third column. So you will know, okay, what type of instruction is that. Okay, so based on this cheat sheet. Or green sheet. Okay, sorry. Let me close the Qt Spring because I was afraid that my PC would get heavier. Alright, let me continue. And then immediate type. So the immediate type includes instruction with an immediate operand, branch instruction, and load and store instruction. Okay, so the word I type means that any instruction that has immediate on that instruction. So for example, ADDI, add IU, like that, NI, okay. So load upper immediate, okay. So all this is I format, okay. So I format, SLTI, or I, what else? Okay, that's all. And then another I format type is branch, any branching. So branch on equal, branch not equal. So that is I type, all right? And then other I type is load and store instruction. So any instruction that has a word load, load byte, load half word, load link, load upper immediate, load word. So all this is an I format. Okay. Also for a store instruction, store byte, store conditional, store half word, store word. Okay, so all this is I format. Okay. Even if it says that all opcodes except 000, this is referring to R format actually. So 001X and then 0100XX. Okay. So all opcodes except these three range numbers are used for I-type instruction. So basically, as you can see, I-type has a lot of instruction actually in this case. Right. So how many fields that we have for the I-type? So we have 4 fields. One is the opcode, RS and RT. So RS is the source, RT is the destination, or what you call as target register. Okay, and then the immediate here means constant. It must be a number. Okay, it must be a number. So that's why we call it as immediate. Or branch displacement or address displacement means the immediate here for branching and addressing is how many for branch is how many instruction that we need to jump. So how many means it is in a number, and then the address is also in number also. So that's why we consider branch and also load word also branching, sorry. Okay, so branching or address displacement is considered as I format. So jump format or jump type, this group consists of 2 direct jump instruction. Okay, only 2. We have J and JAL. So this instruction require a memory address to specify their operand. So J type instruction use opcodes 0001X. Okay, so as you can see, J type only has 2 fields. One is the opcode. So to maintain the similarity, the uniform structure of the MIPS instruction. So that's why each of these format only has one similarities, which is the operation code size. Okay, and then for J type, okay, the rest, okay, after the 6, they keep on the 26 bit to become the target address, right? So all these instruction has their own application. Okay, R type. Okay, so we call it as R type is a non-jump because of they are a register type whereby we execute based on this register. So we are not jumping to somewhere. Okay, so as for the explanation here, so this can be understand when you learn about the lecture whereby this is the data path for each of the stage. Okay, so when we write this coding and when we write these notes, actually it's referring to the slide also. Okay, so and then what we do is that we refer, okay, based on the field here. Okay, so source operand fetch, the 2 source operand are RS and RT. So we know that the source is RS and RT. And then ALU operation is determined by the function Fn. Okay, and then memory access none is because of we only operate within the registers. And then register write, because this is add, okay, for R type. So we have a register destination whereby we need to write the register. So the result from the ALU is return to RD, like that. So in this case, what happened to SA? SA only affect, okay, only there's a value when it is an instruction that has a shift. Okay, then there's a value there, right? So immediate. So immediate, for example, we have ADDI, RT, RS, and immediate. Okay, so in this case, the PC will update PC plus 4, only that normal increment. And then the source operand fetch, okay, they will fetch the RS and immediate field. Okay, and then they would go to the ALU operation. So the ALU operation is determined by the opcode. So depends on the instruction that they need to operate. Okay, so if it's add, okay, if it's an add, so here we will say the add operation, okay, would the ALU would add, okay, the value inside the RT plus immediate, like that. Okay, and then is there any memory access? None. Okay, none if it's an ADDI. If it's a load word or store word, then it depends. Okay, so it will not be none. So this will be explained later on the lecture 9. So and then register write, the result from the ALU will be written to the RT. So this is your register target. Okay, what about branch? So branch referred to the I format, right? So we have opcode, RS, RT, and then immediate. Okay, so in this case, branch would update the PC. Okay, because of we want to jump to a certain level. Okay, so when they want to jump to a certain level, then the value of the PC would be affected. Okay, so if the branch condition is true, meaning if the condition is true, okay, then branch is taken. So they need to jump. They need to jump. Branch is taken means they need to jump. So sorry. Right. So source operand means they will take RS and RT to compare. Okay, here means branch equal means compare if it's equal. So if it's a branch not equal, then it will become if RS not equal to RT. Okay, and then ALU operation, okay, they will subtract, okay, for comparison. So if there is a value, okay, apart from zero, uh, um, so it can be said that it is not equal. Okay, if it's a zero, then it is equal. Just like that. So there's no memory access, no register write. And then another instruction for I format is a load word and store word. Okay, so for load word, okay, they would fetch the RS and immediate, and then add. See here, added to get the memory address. Okay, and then the memory read control signal is sent to memory. So the result from the ALU is sent to memory as the address, and then the data that is retrieved, okay, from memory will be returned to the register target. Okay, as for the store word, okay, no update for the PC because they just add PC plus 4. And then the source is RS plus immediate. And then we would get the memory address. So when they added, they would get a memory address. And then since this is a memory access, so a memory write control signal is sent to the memory. So thereby, they would trigger a control signal so that the memory would be enabled to be written into. Okay, so they would write what are the value from the RT. The content of RT are sent to memory as the write data. Okay, and then register jump, JR. Although this is called a jump, okay, JR here, as you can see, this is a jump register. They want you to jump based on the address in the register of the register source. Okay, so look at the operation here. Okay, so this is the value that is affected. Okay, that is affected on the machine instruction actually. So and then not all of the field here has a value. Okay, has a value. It's because of we have a different type of instruction. Okay, sometimes RS and RT is used. And then sometimes RT is not used. Sometimes RS is not used. They use RT and ship amount. Okay, so it depends on the instruction that is mentioned. So you just need to look at this operation here to know which field would be affected. Okay, when you want to encode your machine instruction. Now you would need to become like a matrix. Okay, so for jump register, okay, what they need is only the RS. So opcode and RS, and then opcode and function. Opcode and function, and also RS. So what about RT, RD, and SA? All become 0. Okay, so the PC would update RS to the PC. And then the source operand will fetch the only source operand that is used is the RS register. And then is there any ALU operation? No, it's because of the only jump. No memory access and only register, no register write. Actually, there is no register write. for JR. Okay. So for JALR, the incremented PC value must be captured before the target address is placed into the PC. So with edge-triggered clocking, this is easy to do, whereby there is an adder to produce the PC plus 4. So basically, we are not considering whatever the value it is. We just need to know what is the machine instruction for that assembly code. Right. So, and then we have a JAL target. Okay, so JAL target JAL. Okay, this one, okay, is a jump register. Okay, jump register. So as you can see here, there's a mistake for this field. Okay, go back to the cheat sheet here. This one is correct. This one. It should be opcode and address. Okay, should be opcode and address. Okay, so next is addressing mode. Remember when I said everything is specified by an address. Okay, so addressing mode are the ways of specifying an operand or a memory address. So the MIPS addressing modes can be grouped into 5 types. Okay, so we have register addressing, where a source or destination operand is specified as content of one of the registers. So 0 to 31. So in this case, let's say if we write ADD register T0, comma register T1, comma register T2. So as you can see here, the operation consisted of 2 source operand. Okay, when I say 2 source operand, it means that they are loaded into the register. So this is what we call as register addressing. Okay, and then the next type is immediate addressing. Even the word here, you should know what type of immediate addressing is, where a numeric value embedded in the instruction is the actual operand. Okay, the actual operand. For example, if I type ADDI, okay, register T0, like that, and then register T1, and then comma, maybe -5. Okay. So if we have like a numeric value embedded in this instruction, okay, such as this -5, so we can consider this is immediate addressing. Immediate addressing. Panjang lah pula. Hold on. Like it. Alright. Now, next is PC relative addressing. A data or instruction memory located is specified as an offset relative to the incremented PC. So, the only instruction, okay, only 2 instructions that can be considered as a PC relative addressing is a big EQ or maybe BNE. So, BEQ or maybe BNE is considered as PC relative addressing. So, for example, is T0 equal to T1 and then jump exit. Like example like that. So, then you should know this is PC, PC relative. Okay, so this is what we call as PC relative addressing. Alright, so that is for the third addressing mode. Now is base addressing, where a data or instruction memory location is specified as assigned offset from a register. So, for example, we use a load word. Just use a load word T0, 4, and then $S0. Now, as you can see, we have a bracket there to show that register, for example, in this case, S0 is a base address. Okay, it's a base pointer. Guys, my laptop doesn't have a Wi-Fi, but can you hear my voice at the moment?
Yes, madam.
Okay. Can Alright. Okay, then I'll just continue. Okay. load word T0 for S0. So as we can see, we have a register that become a base register. Okay, S0, any register that is within the bracket here is considered as a base register. I said base register. Why we call it as a base register? Because it contain, okay, base address. Okay, base address referring to the data memory. Okay, data memory. Okay, so another indicator is that we have an offset here. Okay, so since we have an offset, okay, so we have an offset plus with the data memory. Okay, this is what we call as base addressing. Okay, base addressing. Okay, so load word or store word are those instructions that is under the case of base addressing. Okay, and then the last one is the pseudo direct addressing. The word pseudo there means that it's nearly nearly complete. Okay, nearly complete means that we want to point to a certain addressing. So they use a pseudo direct addressing whereby the memory address is mostly embedded in the instruction. Okay, for example, when we type J loop. Okay, so when you type J loop, then that is pseudo direct addressing. Okay, so anything that needs to jump to any jump instruction that needs to jump to a certain memory address, then we call it as a pseudo direct addressing. Okay, so now let's go to each of these addressing. So register addressing, and in this case it's under the R format. So it's the simplest addressing mode. It's because of all the source comes from the register. Okay, so the instruction will be executed faster in comparison with other addressing modes because they does not involve with memory access. So do remember, because the register is the closest to the processor, then when the data is already on that register, then they can just compute it or they execute it. Okay, so register addressing is the fastest in comparison with other addressing mode. Okay, so consider the following instruction. Now I need to divide it into two. Now get ready with the your pen. Pen and pencil. Okay, it is suggested that you use a pencil because sometimes you made a mistake. You will make a mistake and then you just need to use pencil to erase it, right? So now let's encode. Okay, sometimes the question I would ask you, okay, what is the machine instruction for this assembly code? Just like that question, or okay, construct the machine instruction for the following assembly code. Like that. So if the word asks you machine instruction, machine code, so all those things, anything that referring to the PC is a binary representation. They want you to represent it into a binary. Okay, so let's say we have example for register addressing, ADD register T0 and then register T1 and then register T2. So I would use the same example. So how do I want to know? Okay, so what is the instruction was trying to do is that we know that the first one is the RD. Okay, we know that this is the RD, RS and RT. So basically, how do you want to know that? We go back to the operation here. ADD said that RS plus RT is stored into RD. Okay, so the position here shows that this is RD, this is RS, and then this is RT. Okay, so where is the add? Add is under opcode slash 20 hex here is function. So here we can say opcode slash function. Okay, now you have labeled it based on the position. Okay, based on the position. Now, draw the, alamak, 9:30 ah. Okay, need to finish it earliest. Right, so now draw the R format. So we have opcode, which is a 6-bit. And then RS is 5 bits. And then RT is 5 bit. And then RD is 5 bit. And then shift amount is 5 bits. And then function is 6 bit. Okay, so we know that, for R format, this is an R format, right? So since R format, all the values in opcode will become 0. Then the function will be enabled here. So will be enabled, so we put ADD. Okay, and then where to put the T0, T1 and T2 based on this position. RS is here. So RS is here. RT is here. RD is here. Okay, so T1, T2, T0. Okay, what about shift amount? Because they don't mention any shift amount here. Okay, on the operation, look at the operation, it only say RD is equal to RS plus RT. Nothing about the shift. So then it become 0. Okay, now you have added the instruction. You have put it inside the field. Okay, look at the ADD first. So it start with a 0 on the opcode, 20. If we have a flash there, a slash there, so it means that it's on another field. Okay, so in this case, opcode and function. Okay, so if it must have a slash if it's an R format. So this one become a 0. This one become 20 hex. Okay, it's because of they are written in hexadecimal numbers. So I will write it as a hex to make sure that I'm not forgetting it. Okay, and then what are the value for T1, T2, and T0? Look at the register name here, and then there's a number. So the number here start from 0 to 31. In this case, there are the number here. Okay, the number here is a decimal number. Okay, decimal number. So look at the T. T0 start at 8. So T1 will be 9. T2 will become 10. So we start at T0 here. So T0 is 8. T1 is 9. And then T2 is 10. So shift amount is still 0. Then you can change it to the binary number. Okay. So since the size is 6. So you need to add 1, 2, 3, 4, 5, 6. Like that. Okay, what about 9? 9 convert to binary is 1, 0, 0, 1. And then don't forget, we must have 5 bits, right? So you add 0 on the most significant bit or on the left side. Okay, what about 10? 1, 0, 1, 0. And then don't forget to put a 0 dash to make sure the size is 5 bit. Okay, what about 8? 1, 0, 0, 0. Add a 0 at the front. Then you will get a 5 bits of RD. Okay. Shift amount contains 0. Okay, so contains 0. So you must not only put 1 bit 0, but the size is 5 here. So 1, 2, 3, 4, 5. Like that. Okay. And then 20 hex. So 20 hex must be converted to binary in 6 bit. So 6 bit means the first digit is 4 bit 0. And then 2 here is 2 bit 0. 2 bits. Okay, 2 bits. So 2 in binary is 1, 0. So now if you count all this, you will get 32 bits. of instruction. See, that's how they encode the instruction into a binary numbers. Now you can become a machine. Now you can think like a machine. Okay, so sometimes they ask you, or sometimes the instruction was not written in a binary, so they preferred it to be shortened. So usually when they shorten it, they use a hexadecimal numbers. Okay, so this is in binary numbers. So if we want to represent into a hexadecimal numbers, then you divide it into 4 bits. Like this, like this, like this, 4, 4, 4. And then convert it to hexadecimal numbers, 0, 1, 2, A, 4, 0, 2, 0. So this is in hexadecimal representation. Alright? So I hope you can do this later on, because our exercise will be doing this part. Okay. Although when I written it like this, but actually the 32-bit instruction is basically there's no space there. Actually, there's no space. This is only for the sake of to write it. Okay, to differentiate the field. Okay. So now I can join. Right. So next is the instruction. Let me continue with the next instruction on 944. Alright. So here it's the same as what I've been teaching you, right? Okay, so in this case, RS and RT will be referred to the register file, and then the RS and RT will be loaded to the ALU, and then the final result will be written back to the RD. It should be like that. Okay, so actually the operation is within the register, but not accessing the memory. Okay, and then the immediate addressing. In immediate addressing, the operand is a constant within the encoded instruction. Okay, so instruction will be executed faster because it does not involve memory access, but instead they are only operating using a constant. However, the size of the operand is limited to 16-bit only. Okay, so jump instruction format also falls under immediate addressing, where the destination is held in the instruction. Okay, so let's that one will be in the branching, so I'll just explain it to you later on. So let's do the instruction I format. Okay, so here they are using ADDI T1T11, right? So for the sake of learning, okay, I would use this type of instruction. Okay, ADDI T0, T1, and then this one will be a positive number. I'll put it 5 like that. Okay, so sorry, it's the pen. ADDI, and then register T0, register T1, and then a 5 there. Okay, so we are going to execute this instruction ADDI. So what type of ADDI format? So look at ADDI. It is under I format. Okay, so I format is RS plus immediate. Okay, there's a IMM here, means immediate. Sign extent you will understand later on when you learn about the data path. But actually, they only want to extend the bit to become a 32 bits. So when we have the same size with the RS, then you can do the operation. Okay, so immediate plus RS store into RT. So in this case, T1 is RS, 5 is immediate, and then T0 is RT, your destination. Okay, or in this case, they call it as RT, okay, register target. And then your ADDI become opcode. So no function because this is an I format. Okay, now for I format, okay, you would have opcode 6-bit, and then RS 5-bit, and then RT 5-bit, and then immediate 16 bit. So where do I know? On my green sheet here. Go down and then look at the position. So now I have labeled my instruction. So my ADDI will be here. RS is T1. RT is T0. And then my immediate is 5. Then I need to convert ADDI into a number. So ADDI is 8 hex. So 8 hex. T0 is 8. T1 is 9. Okay, so if you practice this a lot, so you will be able to remember T0 is 8. S0 is 16. Then you just need to add the number. Okay, so since T0 is 8, so T1 become 9. Like that. Okay, now this is in a decimal except for the opcode is in a hexadecimal. Now convert it to a machine code or machine instruction. So 8 is 1000. So since they need a 6-bit, so you add 0 on the left side. Okay, and then 9 is 1001 and then 0 at the front. 8 is 1000. Add another 0 at the front. And then immediate is 5. So 5 means in in binary is 0101. So it means that since this is a positive number, so the front of it is always the 0. So 1010. So since we need a 16-bit, right? So we just continue the 0. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So as you can see, this is a 16-bit. So I'll just separate it based on the space so that I can easily calculate the 16-bit here. Okay, so this is your binary representation for ADDI T0, T1, and then 5. Okay, so that is for I format. Next is basically the instruction is the same. They just need RT. Okay, sorry, RS. Okay, add with the immediate value and then save it back to the RT. So that's how the immediate addressing is done. So base address. So base address is the same as the ADDI except there's a certain condition or the position. Okay, the position of the operand inside of it. Okay, so let me erase back first. Okay, so that you will understand. I'm feeling lazy to write it. So I would prefer to remove it like this. Okay. So hold on. Okay. Kau senang. Okay. Load word. Okay, so check at your green sheet. Where is the load word? So your load word is I format. So I format needs RS of a register. So this become a base register. Okay, and then IMM is the offset. In this case, your offset and then store it in the RT. Okay, so load word. Okay, go back to the your lab. Load word T1, 4 and then bracket T2. Okay, so in this case, this load word is an opcode. T1 is the RT because this is a destination. So we would need to load the T2, the content inside the T2 because this is within the bracket, right? So this T2 become RS. 4 here become immediate. Now the position change. The position change. So immediate is here. RS is here. RT is here. Opcode is here. Okay. Now you can write load word T2. RT is T1 and then immediate is 4. And then look back at the green sheet. What is load word? Load word is 23. So 23 hex. And then T1 is 9. T2 is 10. Because I remember T0 is 8. So when I know T0 is 8, then T1 is 9, T2 is 10. Okay, and then 4 continue. Now you can convert it to binary numbers. So in this case, 23 is 1100, and then 2 here. Okay, so this is one hex is represented by 4 binary digits. So for 2 here, we only need to represent only 2 bits because we only need 6 bits, right? So 2 is 10, like that. Okay, for 10 here, please remember, if I did not write any 10 or if I did not write any hex or binary, then this is a decimal number. Okay, so decimal number. So the binary number is 1010, and then put a 0 at the front. Okay, 9 is 1001. Put a 0 at the front. Okay, 4 here is 100. Okay, so just put a 0 to make it a 4 bits, and then the rest become all 0. So 12 bits of 0 is extended on this, is put inside this immediate field. So now you will get your load word machine instruction. Okay, so this is in binary. Okay, that is for the load word if the offset is a positive number. But sometimes, sometimes the memory is scattered somewhere. Okay, it's scattered. Okay, or maybe it was placed at the top. So they need to go back to the top. So the instruction is executed in a linear form. They go to the next down, next down, next down. Okay, so since the memory need to be accessed like this. Saya nak tunjuk. This one. Okay, so let's say the base address is here. So the effective is here, somewhere at the top. So if it's somewhere at the top, then the offset become a negative. Okay, the offset become a negative. So to become a negative, so in this case, you would need to 2's complement decimal 4. Okay, you need to 2's complement the 4. So I'll put a 4 here and then with a negative. So you can see the 2's complement for negative 4 is 1111, and then at the end of it is 1100. So I will write it like that. So 1100. Okay, if it's a negative, if it's a negative, so 1 2 3 4, 1 2 3 4, 1 2 3 4. So this is in the case that if it's a negative number. So you must put a 2's complement to represent this negative, right? So that is for load word. So I don't need to teach you for the store word. Basically, it is the same. Okay, so if it's a store word here, okay, if it's a store word, this become RT, this will become immediate, and this become the RS. Okay, so basically it is the same. Okay, so next is the PC relative addressing. This one I need to draw back again. Okay, so PC relative addressing is for branching. Okay. Conditional branches, PC would refer to a special purpose register, program counter that stores the address of next instruction to be fetched. Okay. So in this case, when the branch is taken, the PC need to jump to that branch. Okay. So in this case, you need a set of instruction. So for you to count how many instructions that you need to jump. Okay, so I will refer to this example of PC relative addressing. As you can see, there's an instruction BEQZ, register T0, and then string N. Okay, it's on the instruction 004000028. Okay, so this is an instruction address. So it contains this branch instruction. So when we have this branch instruction, we need to know where does it need to jump to if the branch is taken. So BEQZ T0 string N. Where is the string N? It's on this address 004000034. Okay, so remember when I teach you during the lecture, okay, to count how many instructions that they need to jump, okay, ignore the current instruction. You are at the 28, right? You are at 28. So you will count the next instruction, which is the 2C here. Okay, as count is equal to 1, count is equal to 2, and then there here is your string N, count is equal to 3. So you should know your string N means you need to jump or you need to branch 3 instruction from the current instruction BEQZ. Okay, so I'll write the instruction here. BEQZ. Okay, register T0, register, sorry, no register, sorry. Okay, register T0 and then string N. Right, but if you look at the green sheet here, there's no BEQZ. Okay, at the moment there is no BEQZ. Also here, the pseudo instruction set also doesn't have BEQZ. It's because of it's a subset of a branch in MIPS instruction. So the current QTSPIM would convert this instruction to the basic branch equal instruction. So the equivalent for this instruction is, because they are referring branch equal 0, means is T0 equal to 0. So we can also represent it as branch equal 0, register T0, register 0, comma, string N. Okay, register 0 means 0 lah. Alright, so this is the equivalent of instruction for this BEQZ. Okay, so now you need to label it. Which one is opcode? Okay, BEQ would become opcode. T0 and register 0 will become what? Okay, go back to the instruction green sheet here. BEQ, it says RS is equal to RT, then we need to jump. Okay, so here says this is RS, this is RT, and then this is your immediate. How many instruction that you need to jump to go to the string N. So you will write your, okay, draw your field of code RS, RT, and then immediate, which is 16-bit. Okay, so BEQ opcode is 4 hex. Okay, 4 hex. And then your RS is T0, RT is register 0. Okay, register 0. I don't need to put a register anymore. You just need to put the value of the register, okay? So, register 0 is 0. Okay, look at the register name. Register 0, number 0. So, it's number 0. And then your immediate is the string N. So, count the instruction that you need to jump. So, this is your current instruction. This is your current instruction. So, we count the next one is count is equal to 1. Count is equal to 2. Count is equal to 3. So, your immediate is 3. Okay, your immediate is 3. So, now you can convert it to binary. So, 4 is 1, 0, 0. And then complete it to 6-bit, 1, 2, 3. And then T0 is 8. So, 1, 0, 0, 0. Then put a 0 at the front. RT is register 0. So, 1, 2, 3, 4, 5. 5 bit 0. Okay, to tell that the value of the register is 0. And then immediate is 3. So you will put a 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so this is your branch encoding. Okay, branch encoding. Right. The next part. Okay, so as you can see here. Okay. Let's compare. Let's compare. Okay, string n is here. Your 0 is here. Your rs is here. And then your op or your beq is here. See? And then, how do they calculate the branching? So what they do is that they take out the immediate value here, sign extend, and then put an extra bit 0 there. Okay, sign extend to make it they shift by 2 means that they add 2 bits at the right side. Okay, at the right side. So if you add 0 at the right side, so it means that you shift to the left. And then sign extend to become a 32-bit. Okay, and then you can add with the program counter so that you will get the effective address of the instruction that you want to jump where the string n is. That's how you want to encode the PC relative addressing. Okay, last is the pseudo direct addressing. I need to finish it. So we don't have any example for this. Okay, so I would need to refer to the mana slide. Where's the slide? Where's the slide? Alright, here. Okay, so before we start for the J format, this one, I would refer to this instruction. Where is the? Tak ada. That's okay. We will just refer to this instruction. So, where is the PC relative? Okay, this one. Right. Okay, I'll go back to the notes here. So, pseudo direct is specifically used for J-type instruction, J and JAL. So, the instruction only consists 2 fields, one is opcode and 26 bit for the immediate value target, whereby they are referring to the program counter. Okay, the program counter of where do you want to go to? Okay, where do you want to go to? So I would refer to this slide, okay, and write the command. Okay, write the command together with the memory address. Okay, so let's say we start at 0040030 like that. Betul ke? Tak cukup. Hold on. Hold on. 00030. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And then we will have a loop. BEQ. Okay, register 9, register 0, END. And then 0040034. This is a PC content no, memory address whereby the PC will fetch. Okay, the PC would fetch each of these memory address. Okay, so we have ADD. And then next is 3, 4 plus 4 is 3, 8. Okay, 3, 8. So this is ADDI. And then next is 0040008 plus 4 is C, 3C. Okay, so this is J loop. Okay, so this is your J loop. And then the last one is 0040040. Okay, so now this one is your N. Okay, I'll just put it N there, like that. Okay, so we want to execute the J loop. Okay, so where is the loop? The loop is here. Okay, loop is here. So we will need to take out the memory address for this instruction where it contains the label loop. Okay, so you need to refer to this part. Alright. So once you have know the content of the memory address for that instruction, then you can put your you can encode it. Okay, so J loop. Okay, so here is your opcode. This is your target address. So how do I know? I refer it to my green sheet here. See opcode and address. So look at the jump. Jump here says jump address or your target address need to be loaded to the PC. So it means that it must have an 8 hexadecimal address or maybe 32-bit address. But in this case, it is a pseudo direct addressing because it only contains 26-bit only. So you draw the opcode and then target address is 26. Opcode is 6. Okay, so your opcode is J and then your target address, your loop. Okay, your loop is on this address 00 ni. Follow the arrow here. Follow the arrow, so it is here. So 004 00030. Still, you need to do something. Okay, so jump here means command. What's the number for jump? Is 2. Okay, 2. So 2 hex. Okay, 2 hex. So for loop, okay, for the looping, okay, so for the looping, you need to look at the instruction of J format. Here, since the loop, okay, is on this position, so we need to extract the memory address to become a binary numbers. Okay, so extract each of these hexadecimal address to a binary. So 0, 0, 0, 1, 2, 3, 4, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 3, 0, 0, 1, 1, 0, 0, 0, 0, like that. Okay, so now to calculate the target address, okay, take out the 27 starting from the 27 bit. Okay, this is 31, 30, 29, 28, and then this is 27. So starting from 27 until bit 2. Okay, bit 2. So until this part. So you would take out this part. You would take out this part become your target address. Okay, so now you can write your encoding, okay, your machine code. So 2 hex means 100000. So now we have 6 bit, and then your target address is the one that you have draw here. So you just continue 000 0100 0000 0000 1 2 3 1 2 3 0011, and then only take this 2 bit 0 0. So this is 26, this is 6, 26 plus 6, you will get 32 bits. So that's how they encode the instruction from this command JLoop. So provided that you have a collection of instruction and also the memory address for each of the instruction, then you can calculate your branch and also your loop. Your jump. Okay, so that's it for today. I've extended it to 10 minutes, right? Sorry. Okay, so now you can go to the lab assessment 8 here. Then you can try to attempt. Okay, you can try to attempt the instruction. Do I need to preview? I don't want to. Okay lah. I start attempt je. Okay, basically the question is the same. Question is the same. But in this case, they were asking you from the instruction, blah, 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 right? So it says here, you must refer to the instruction address, okay, and then refer that instruction and then answer the questions. So in this case, refer to the address 0040024. So what instruction is that? So here, ignore the label. Ignore the label. So only take out the SLL, T1, S3, and 2. Okay, so what type of instruction is that? Go back, search SLL. Here, it is an R format. So the question asks you the instruction is an what format instruction. So you just need to type that part. And then based on the previous answer, so if it's an R format, calculate and fill in the space, okay, of the binary number per field representation, okay, so that you need to assemble the instruction to become a machine code. Okay, so let's say if it's an I format, so I format only needs 4 field. Okay, only 4 field. So in this case, if there is no answer for that field, just put a dash. Okay, so I've given you unlimited access. Unlimited access means that you can try again and again later on. And also you can go back if you feel that you are giving up because you still don't know the answers, okay, because you already calculate it, you already draw it on paper, okay, and then let's say you have the answer. Once you have the answer and then you put it on this field here, okay, you put it on the field, but still the answer is wrong, then you can just look at the review, okay, let's say let me go back like this, and then I can just look at my review. Okay, review respond, and then as you can see, oh, there's a wrong here, and then there's an answer for that. Okay, for me to refer, why the answer is this? So that you can go back and then try to answer on that paper. On the paper, okay, try to find back again what are the position based on my answer. Okay, so that's it for the lab assessment. You were given a 1 hour, okay, to complete this. Okay, but actually you can go back at home and then try back again later on. That's okay, but I would ask you to do this because of we only have this session, okay, for you to answer the question, and then ask me if you don't understand it, right? And then once you finish it, okay, try to answer the survey question. This is not a survey, actually it's only a yes or no. So do you like this type of assessment? If it's yes, I would try to give this kind of question again later on the next week, next week. But the drawback is that the advantage is that you would know how to answer the question, but it's not representing the whole instruction, the whole questions. Okay, the whole questions for your final exam. Okay, so it's not, but it's only a portion of it. So how do you want to get to that answer? So you would need to do this exercise. Okay, so I will leave it up to you. If you have a question, post it to the comment or maybe unmute yourself. Okay, please wait. All right, so chop, try it now. Okay, so I will be here. Okay, that's all.
Thank you, madam.
Right. So, is there any problem when you try to answer the questions?
No, madam.
Oi, bagus. Siapa ni? Wafil. Oh, Wafil dah siap. Okay.
Madam,
Saya
nak tanya soalan 4, madam.
Soalan 4. Hold on. Soalan 4. Yes. What's wrong? Soalan 4 apa ya?
Dia punya
3-0. Exit tu salah kira. Exit.
Saya tak perasan ada exit bawah. Saya tak perasan ada exit dekat line last sekali.
Habis macam tu. Kosong boleh tak kosong je semua. Mesti kena jam.
Sebab silap.
Dia consider exit ni ada lagi instruction tapi dia orang tak nak letak. Macam tu. Dia considered an instruction lah. Selalunya label tu dia nak letak sebab kita they want to know where to jump tu. So the acceptor tu kena jump. You have to jump. So when you want to jump, you consider this is a line of instruction although it was not encoded. Exit ni will not be encoded lah sebenarnya. It will not. It was supposed to have like another instruction there. So let's say exit is here, right? Exit is here. So when you want to branch to exit, so you need to count 1, 2 and then 3. So count this as a one line. So one line and then this is 3. So 3 is 1, 1 lah. Macam tu. And then as for this one, you miss out the 1, 0. So they will calculate how many bits that you have. So this one is 5. So you are supposed to put 6 lah kan? Okay? Yang lain tu okay.
S5 ni? Kenapa?
Mana?
S5 RT
S5 is
bukan 20
S5 is
21 eh?
21 go 21 is decimal. In hexadecimal it is 15. So that's why saya dah perasan. Actually university you think that this is a hexadecimal number and also the number is 6 bit, so that's wrong. Go back to the green sheet there, you can see 21 and then just take out the 5 bits on the right side, from the right side, and then calculate the 5 bits. So 10101. Okay, so use calculator lah. It's because of the number of the registers, okay, is always decimal number.
Okay.
Okay, only opcode and function hexadecimal number. Okay, but sometimes I will give a trick. For example, the load word here is very simple, right? Question mana load word 1, 2, 3. So question 3. So your question 3, your this one is correct, okay, except for your load word here. Why is it again wrong? 23, you know? Load word. I say man. Supposed to be. Yeah, betul. 23. Okay. So check back again And then the question for the load word can be very I can change the number. For example, the immediate here can be replaced with a hexadecimal number. So to give you like some tricky part. So I can just give you like a C here. C means 0xC. I can write it like okay, load word can be written as load word. Hold on, my monitor I see me. Okay. T0 and then I can write it like this. 0xC like that. Okay, and then register as 0. So the immediate number here can be represented using a decimal or hexadecimal. So if it's written as C here, then you should know what to put on the immediate for C. Right? Understand? So here C here is referring to the hexadecimal, right? So, kalau dia hexadecimal, if it's an hexadecimal, so load word like that, and then P0, and then 0xC, and then register as 0. So, the opcode ignore, and then RS, RT, and then your immediate. So, your immediate is here. So, C can be represented as in binary as 1100, and then continue like that. So, so this number for the immediate can be hexadecimal and also can be a decimal number. So depends on the representation of the front of it. This one. If I just put a 12 there, then that is a decimal. But if I put a 0x, then you need to convert it from hexadecimal to binary numbers. Like that. Okay? So that's one of the thing that you need to remember for that question. I think the rest is okay. No problem. So that is for siapa punya tadi saya check kan? Wafir. Balkis is on our class tu. Kejap. Check. Balkis. Tak. Oh ada. Balkis. So let's see Balkis punya. So Balkis. Yeah, okay. For the, I know why. For the shift left logical, the mistake here is that you need to look at this one. Shift left logical. Okay. So only have RT as the source and also the shift amount. Okay, RT and shift amount. So for this kind of instruction, okay, let me select. Okay, let me close back. Okay, don't want to see it. So now, so if it's written like this, shift left logical, T1, S3, and then 2, right? So shift left logical is opcode and function, and then this is RD. Because of this is an R format, SLL is an R format. So T1 become RD. Okay. S3 will become, where is shift left logical? RT. So S3 will become RT. And then 2 here is the shift amount. So your opcode, then your RS, your RD, RT. And then RD, and then shift amount, and then function. So look at your shift left logical, 0 and 00 hex. So your opcode is always 0, your function will become 00. And then where is your RS? It doesn't mention here, right? That's not labeled as in the operation of the SLL. So RS becomes 0. And then this one, RT is your S3. RD is your T1 here. And then where should I put 2? To the shift amount. And then is this a decimal or hexadecimal? So if it doesn't have an 0x at the front of it, then that is a decimal. But if it's written like this, then this is a hexadecimal number. Then you need to write like this. Hexa. Okay. But at the moment, it doesn't have 0x at the front. So this is a decimal number. Okay. So then that convert it to the numbers, then you would be able to answer for these questions. Okay, for this part, this one is correct. Okay, only T1 is correct. The rest was not. Right? So that one, I don't think you have any other problem for that. Also for this part, which question is this? Load word. Okay, for load word, why this one is correct, this one is incorrect? It's because of T0 is the destination as RT. T1 is your source, right? So if T0 is 8, then T1 should be 9. Okay. So make sure you calculate it correctly. Okay, or maybe what you can do is that when you are trying to encode it to a machine instruction, then list out T0 until T9 number representation, and then that will be easy for you. Just list out like okay, so T0 is 8, T1 is 9, T2 is 10, and then T3 is all the list of registers that you might use during your assembly coding. Okay, so that's it. Okay, so that's the end. It's 11:04, so I'll stop now. Once you have finished it, I would like you to answer the choice question, the survey question. Do you like this type of assessment? All right. So that's it. I'll try to give more exercises for this part, whereby it will only assess you based on the answers, but it does not assess you the steps or the process within of it. Okay, so do remember during our final exam and also other assessment, actually the process is important. So I don't want you to not to know what are the answers. So that's why I've given you this kind of assessment. Okay, but for a final question, this is only a portion of the final exam questions. Okay, so practice all these things so that you will be able to answer the questions later on. All right, so since there is no questions, I would end the session. Today. So I'll see you tomorrow. Okay, bye-bye. Assalamualaikum.
Salam. Thank you, madam.
Welcome.
Thank you, madam.
Thank you, madam.
Thank you, madam.
You're welcome. You're welcome.